Good evening, everyone. Welcome to the first talk from 2022 of the Yorkshire Local Centre of the Royal Meteorological Society. My name's Ben Pickering. I'm a research fellow at the National Centre for Atmospheric Science, and I've been on the Yorkshire Local Centre Committee since 2018. I mainly research precipitation processes, but I'm transitioning to develop autonomous atmospheric profiling drones as well. I'm joined tonight by my fellow committee member, Carmelika. Good evening, Carmelika, who will be monitoring the chat and highlighting your questions, which will be answered at the end of the talk. So first of all, some logistics for the event. The talk is going to last approximately 30 to 40 minutes, followed by a max 15 minutes or so for any of your questions or comments. You can put these questions and comments in the chat box on the right-hand side, and Carmelika will be monitoring the chat and marking these questions throughout, and we'll do a Q&A session at the end of the talk. You will be able to rewatch this event from the Royal Meteorological Society YouTube channel, where it will be uploaded in the next few days after the talk. So now on to the main event. Tonight we have a wonderful talk brought to us by Dr. Simon Lee. If you'd like to come on screen now and say hello to everyone.
Good evening, I guess, to most.
So Simon studied the Masters of Meteorology and Climate integrated master's degree at the University of Reading from 2014 to 2018, a part of which he spent a year at the University of Oklahoma. Simon then went on to do a PhD, also at Reading, with some co-supervision at Oklahoma, and graduated in 2021. He became a postdoc at Columbia in November. Simon is also co-editor-in-chief of the Weather Journal, and fittingly for a Yorkshire Local Centre meeting is from Harrogate, though he worries that his accent may have been diminished by years of living in Reading, Oklahoma, and New York. And I'll let you say the phrase.
Hey, oh.
Well, I'll hand over to you now, Simon, and go ahead. The floor is yours.
Fantastic. Thanks, Ben. Thanks for the introduction. And thank you, everyone, for coming from around the world, around the UK, and whatever time of day it is. Good evening, good morning, good afternoon. It's just past 2 here in New York. And so today I'll be talking about how the polar vortex influences your life in winter. And I thought I'd title that talk in a bit of a more personal sense, how it influences your life in particular. And here's a nice wintry scene that I took a couple of weeks ago in Fort Washington Park during Manhattan's first big snowfall event of winter. And I know that this is a scene that many of you in the UK and in other parts of the world are longing for, as some parts of the world have not seen much snow this winter. So Ben's already given a good bio for me, but a bit more about me. I like to think that I first became interested in weather in 2003. The reason I say that is because I can distinctly remember cutting out headlines about the heat wave in the summer of 2003 and sticking them in a scrapbook, which seems like quite an outdated idea now. And I know I was interested in the weather in 2004 because I remember the Boscastle flood and being interested in that and the hurricanes in the Atlantic that year. I then traced my interest in the stratosphere back to 2009, when the Met Office released a press release with what I thought at the time was a really fascinating diagram about how the stratosphere influences the weather that we have at the surface, and that just captivated my interests. In 2014, I went to Reading, did the RMetS with a year in Oklahoma, and then decided to stay, do a PhD at Reading as well, became co-editor-in-chief of Weather alongside Eddie Graham in 2020, and then I completed my PhD in October 2021 and moved to New York in the November to start a postdoc at Columbia. And before I start talking about all kinds of stratospheric things, I thought I'd illustrate this talk with some real world weather, which is this nice photo of a tornado I took in May 2019 in the Oklahoma Panhandle. It's also in the frontispiece of a book by John Shunk, which I recommend. Anyway, so what I'll talk about today is what the polar vortex is, and also, I suppose, what it isn't. There's some misunderstandings about that have been propagated by the news media. I'll talk a bit about variability in the polar vortex, how it comes about, and why that's important. I'll talk about why we care, which is fundamentally, I guess, why you would want to come to a talk about this, which is stratosphere-troposphere coupling, and how the stratospheric polar vortex influences the weather that we're experiencing, influences your life. and then talk a bit about the predictability of the stratosphere, and then finish with a look at this winter so far. And when Ben first invited me to give this talk, I was thinking, wow, giving a talk on the polar vortex in the middle of winter, I wonder what situation we'll find ourselves in and what I'll be talking about. And here we are. So what is the polar vortex? Now, to understand that, we have to think about the polar night. So during winter, the poles obviously receive much less solar radiation than the tropics. And in fact, in winter, the polar region receives none. That's the polar night. And that leads to rapid cooling of the polar region with respect to the tropics. And in the stratosphere, that's particularly effective because the stratosphere is dry. There's no clouds. It's far away from sources of heat from the ocean or from the land surface. So you get rapid cooling in the stratosphere over the pole compared with the equatorial region. And that leads to a strong meridional temperature gradient. And on these sort of large scales, thermal wind balance acts, which leads to a strong westerly jet stream forming in the stratosphere. And that's the polar night jet stream, which encircles the pole. And so effectively that jet stream and the cold air poleward of it is the polar vortex, which is essentially this planetary scale vast cyclone that sits over the wintertime pole in the stratosphere. It's about 10 to 50 kilometers above the surface. And that's pointed out in the diagram on the right, which is showing the zonal mean zonal winds as a function of height and latitude. And you can see the polar vortex there in the blues in the wintertime hemisphere. Now, in the summer, that poleward temperature gradient that drives the polar vortex's formation is reversed. So you end up with easterlies in the summer stratosphere. So the polar vortex is exclusively a wintertime phenomenon that's fundamentally forms because of radiative cooling. Now, you will note from the figure that the blues in the top panel are of lighter shading than the blues in the bottom panel. The Arctic polar vortex is weaker than the Antarctic polar vortex, and I'll mention a little bit more about that shortly. So enough of the zonal mean cross sections. What does that look like in space? Well, this is just an example of the Arctic vortex on the 12th of March 2019, shown on an isobaric surface on the 10 hectopascal pressure surface, which is at about 30 kilometers. And you can see the polar vortex sitting there almost slap bang over the pole and encircled by that polar night jet stream. So what isn't the polar vortex? I said I'd mention that. And I had a great time going and hunting down some news headlines from the last 8 years or so. Now, confusingly, the area encircled by the tropospheric jet streams, the cold air poleward of the tropospheric jet streams, is sometimes referred to as the tropospheric polar vortex. And then what that meant was that when you had a large-scale meander in that tropospheric jet stream and that cold air spilled equatorward and persisted for a long period of time, somehow that got translated into the media as the polar vortex or a polar vortex arriving at a certain location. And the first real instance of this was 2013-14 when there was a large-scale meander in the jet stream over North America, led to extremely cold conditions in the eastern half of the country. And you might remember seeing scenes of Niagara Falls frozen over. And that just became known as the polar vortex has arrived in the northeast of the US. And so there were various headlines like polar vortex death toll. That's from a similar cold wave in early 2019. The Daily Express, of course, in the UK like to just use capital letters and capitalize words that have no real consequence, like hours is not the most important word in that headline, and yet there we go. But I'm sidetracking myself. Point being is that this is kind of a confusing use of the term. And so when I'm talking about the polar vortex, I'm talking about the thing in the stratosphere, essentially the original use of polar vortex. And I don't think what's in the troposphere should be called this. That's not it. And if you are interested in more on that, Gloria Manny and colleagues have recently submitted a paper to GRL, which is on ESAW, the preprint archive, at that link, and I'm sure you can find that later. So that's what the polar vortex isn't. Now, defining the strength of the polar vortex, that's typically done by considering the zonal mean zonal wind. So that's the longitudinally averaged west to east wind at 10 hectopascals and 60 degrees of latitude. It sounds like quite a simple diagnostic. It is. More complex diagnostics, it turns out, actually correlate really well with that. It's effectively chosen to capture the center of that polar night jet at an altitude that varies sufficiently to capture the large-scale vertical structure. And so in the histogram here, I'm showing the wintertime distributions of this zonal mean zonal wind at 10 hectopascals and 60 north in the blue and 60 south in the orange. And so what you see is not just that the Antarctic vortex is on average stronger than the Arctic vortex, about 40 meters a second stronger, but it's also much less variable. You have a much more compact distribution, narrower. It's more leptokurtic, whereas the Arctic vortex is much more spread out. And you even have easterlies, which is ringed there in red, and that's an important aspect of the Arctic variability. So what determines this? Why is the Antarctic so much stronger? Why is the Arctic so much more weak and varied? Now, there's a lot going on this slide. There's a lot of text. I do apologize, but we'll get through it. So the stratosphere is influenced by vertically propagating Rossby waves. So Rossby waves, those large-scale meanders in the mid-latitude jet stream, we regularly watch those on weather maps propagate from west to east or east to west, depending on the flow, as large-scale ridges and troughs that we experience. But they don't just propagate horizontally towards the pole or from west to east, they also propagate vertically. Now, I found this quite hard to work out what figure to use for that, because 3 dimensions are difficult to show on a 2-dimensional surface. But what the figure shown here is trying to do is to show this wave structure on a day in early February 2018. These are the eddy heights. They're the departure from the average height averaged across 40 to 80 north as a function of longitude and pressure. So you can see those waves. And hopefully what you can see is the reds are the ridges and the blues are the troughs. And you can see that there is a wave structure that exists all the way from the troposphere up into the upper stratosphere. Now, only the longest waves can propagate from the troposphere to the stratosphere. These are typically those with a zonal wave number, so that's the number of ridges and troughs you can fit around a latitude circle of between 1 and 3. And they can only propagate into regions where the winds are westerly, which is essentially because you need a positive poleward potential vorticity gradient. That aspect is important. And these waves, because of the exponential decrease in atmospheric density with altitude, these waves grow in amplitude as they propagate upwards. You can see that as the increased saturation of the colors there. And as they grow in amplitude, rather like watching a wave rear up as it approaches a beach, they can do pretty much exactly that and then overturn and break. And in fact, that analogy that this process is like waves breaking on a beach, I think dates back to a 1983 Nature paper by Michael McIntyre and Tim Palmer. So not a new analogy. And so when these Rossby waves break in the stratosphere, they exert a westward drag, so an easterly acceleration on the westerlies, decelerating them. And that essentially, that aspect of the balance between these breaking waves and the otherwise radiative cooling of the vortex is what leads to this variability in its strength. An important point is that these upward propagating Rossby waves have to have positive eddy heat flux. Positive eddy heat flux means an upward propagating Rossby wave. And so on average, the vortex strength on any given day is strongly related to the amount of eddy heat flux into the stratosphere in the preceding weeks to months. So you'll hear a lot about eddy heat flux when talking about the strength of the stratosphere. Now, that all-important question about why is it the Northern Hemisphere where we see all this variability essentially comes down to what the Northern Hemisphere has, which the Southern Hemisphere doesn't. And that's continents, mountains, land-sea contrast, all around the mid-latitudes, all in that mid-latitude flow, disrupting it and generating large-scale stationary waves in the troposphere, which can propagate upwards into the stratosphere. And so the mean state in the Northern Hemisphere is much more wavy than the mean state in the Southern Hemisphere, where you have a jet stream that can essentially, because of the Southern Ocean, move all the way around Antarctica free of these large-scale disruptions. And so that's what the figure on the right is showing. These are 500 hectopascals. These are effectively the mean stationary waves, and you have clear stationary waves such as the one forced by the Rocky Mountains, for example. And then there are phenomena in the troposphere that can amplify or suppress this, such as blocking, such as the effect of synoptic scale weather systems and waves, the Madden-Julian oscillation, that 30 to 60 day band of tropical convection, or El Nino and La Nina. Basically anything that can impact the wave structure of the troposphere can then act to suppress or amplify the amount of wave activity that the troposphere is generating. And so an extreme case of stratospheric variability is the sudden stratospheric warming, or SSW. Occasionally, in older literature, it's called a stratospheric sudden warming, but either way. This is essentially, I like to think of it as like the Ron Seal of stratospheric events, because to describe a sudden stratospheric warming essentially involves saying it's a sudden warming of the stratosphere, but essentially it's an extremely weak polar vortex state. And the term SSW is often used to mean a specific subclass of these, which is a major sudden warming, which is defined as a reversal of those 10 hectopascal 60 north zonal winds, or 60 south, to easterlies during winter. So a complete turnaround of that jet from the polar night jet as being westerly to easterly. And because we're talking about thermal wind balance on these large scales, that change in the wind is associated with a rapid warming of the polar region in order to reverse that temperature gradient. And now when I'm talking about a rapid warming, it really is, it's monumental just how large and rapid the warming of the polar stratosphere is during a stratospheric warming. And so the figure on the right is looking at the evolution through the winter of 2008 to 2009, and showing the evolution of the January 2009 SSW, which is the one that I credit with my interest in the stratosphere. It turns out this was one of the most extreme SSWs that's been observed. And so in the top panel, we see the polar cap average temperature at 10 hectopascals. And you can see that through the winter, that cools on average with radiative cooling. And then in this case, on the 24th of January, the temperature skyrocketed from about 200 Kelvin to about 250 Kelvin. So in the space of a few days, it's a huge explosive warming of the stratosphere. Actually, explosive warmings is what these were called when they were first discovered in the 1950s. And then associated with that in the bottom panel, you also see this tremendously fast deceleration of the winds here from about 70 meters a second, and in fact a record strong vortex, all the way in this case to a record weak vortex. And actually the most easterly wind observed in the stratosphere in the last 4 decades or so of minus 30 meters a second. So tremendous planetary scale reversal of circulation, a really extreme event, which is why these are so captivating. And since 1979, there have been about 27 of these major sudden warmings in the Arctic stratosphere, which equates to about 6 per decade, or about once every other winter. I think that's fairly common for something of this scale, which is a good thing, because it means we get a larger sample size with which to observe these. In the Antarctic, where the vortex is much stronger, there's only been one, and that was in 2002. There was something close to a major warming in 2019, but it didn't meet this definition at least. And if I'd been giving this talk a year ago, we'd been talking in the aftermath of a major sudden warming. There was a sudden stratospheric warming on the 5th of January 2021. That's the most recent one. And so during these warmings, the vortex is disrupted, and it can either be split into two, or it can be displaced off the pole, and that's what this figure here shows. You see the inactive polar vortex, the black lines delineating the edge of the vortex. In the inactive vortex, you see those encircling the Arctic. In the displacement, the vortex is shunted off the pole towards Eurasia in this case, and in the split, you have the vortex splits into two smaller vortices, one over Eurasia and one over North America. In a vortex split, that's always pretty much the way the vortex will split because of the orientation of the stationary waves in the atmosphere. That's the way it will split. You won't see it split the other way around. And so when we get this major SSW, we generate easterlies. Now, you might remember from earlier that I said that Rossby waves can't propagate into easterlies. They have to have westerlies. So once you have this layer of easterlies in the stratosphere, that acts as a shield. That's a layer beyond which Rossby waves can't propagate beyond. And so any subsequent waves propagating up reach this layer of easterlies, and they can't, what do? They have to brake, and so they decelerate the winds below that level. And you get this critical layer interaction, as it's called, which brings down that deceleration through the depth of the stratosphere. At least that goes back to the Matsuno model from 1971. And so once you've had that effect of decelerating the vortex right through the stratosphere, you then don't have a polar vortex anymore. And the vortex needs time to recover. And so the figure here is a time height cross section of the polar cap geopotential height anomalies, effectively proportional to the temperature. And you can see that warming in late January propagating down, almost looking like a foot stamping down from above. But then this extended period of time that it persists for. And that's from late January through to the end of March in the lower stratosphere. It's a long time. And the vortex needs time to come back, to recover. You need to cool away, radiate away this warming and re-establish the vortex, which happened after this 2-month period. So these are long-lasting phenomena. Now, the opposite in some sense of a sudden warming is a strong vortex. When the wave activity is anomalously low, then that radiative cooling can dominate. There are some other ways that this can happen, but essentially, if you've got fewer waves, then you can have that radiative cooling strengthen the vortex. In general, these are considered slightly less interesting because they're just not explosive and dramatic. They're slightly less well researched, less well defined. But the reason I wanted to mention them is because you might have noticed all those blues in that figure from earlier. And that's the strong vortex that followed the SSW in 2009. Really, because when you have an SSW, because you're shutting off, you're generating these easterlies and shutting off the stratosphere to the influence of any upward propagating Rossby waves, you can establish a very strong vortex aloft radiatively. And so sometimes you see SSWs followed by a much stronger vortex several months later. And that's what happened in 2009. So the stratosphere is not Vegas. What happens in the stratosphere doesn't stay in the stratosphere. And that lends itself to these so-called dripping paint plots. Now this figure is somewhat worryingly more than 20 years old now, which is weird to think about, but essentially it's showing how you have this phenomenon in the stratosphere, be that a strong vortex or a weak vortex, propagating downward, but then occasionally influencing the troposphere below, dripping down into the troposphere, which is effectively below the thin horizontal line. And that's why this is interesting. So to understand this coupling, we have to think about something called the Northern Annular Mode, or the NAM, which is the leading mode of mass variability between the mid and high latitudes. And what that means is essentially you have opposite signed pressure or height anomalies between the polar cap and between the mid latitudes. And this is a vertically deep phenomenon. This extends through the depth of the stratosphere. And so in a positive NAM, you have lower pressure over the Arctic and higher pressure in the mid latitudes. I should say it's anomalously so. And in a negative NAM, you have the reverse. You have a high over the Arctic, an anomalous high over the Arctic, and anomalous lows in the mid latitudes. Sometimes this is called the Arctic oscillation NAM, and then in the North Atlantic sector, which you'll see from the figure, is potentially the most important part of this pattern. It's called the North Atlantic oscillation, or NAO. It's essentially a regional subset of that variability. Now, I mentioned it's a vertically deep structure, so what that means is essentially the strength of the stratospheric polar vortex is the northern annular mode in the stratosphere. The strength of that jet at 10 hectopascal 60 north is proportional to the 10 hectopascal northern annular mode. So if the jet is stronger, that's a positive NAM. And then if you do, in a really basic level, if you do a regression of those stratospheric zonal winds or that stratospheric NAM with the surface pressure, the pattern that you recover is just then the surface annular mode pattern. So what that means is that the sign of the tropospheric annular mode is on average shifted toward that of the stratospheric annular mode. And so the anomalies in the polar vortex are expressed in some of the similar sense in terms of the surface weather. And if you have a negative NAM, then you're more likely to have cold air outbreaks around the Northern Hemisphere mid-latitudes and equator with shifted jets and storm tracks and impacts on real world weather. And so that's really almost in a sense, the answer to the question that I posed as the title of this talk. But what's particularly interesting and particularly useful when it comes to the impact of the stratosphere is that the anomalies in the polar vortex strength are very persistent. So the time scale of anomalies in the vortex in the lower stratosphere in midwinter, as shown in the figure here, is over 4 weeks, about 30 days. And what that means is that this is a much more persistent phenomenon than any tropospheric weather pattern. If we know the vortex state today, we have a much greater idea what it's going to be like in 1 or 2 weeks, or even longer ahead of time. And that means it's a potentially much more predictable phenomenon. But it also means it can act as a boundary condition to the troposphere that bridges the gap between weather forecasts that are 1 or 2 weeks and seasonal forecasts that are on a scale of months, right in that subseasonal range between the two. And that's where it's particularly useful for bridging that gap, because 4 weeks is bang on the subseasonal timescale. And so there are cases within all that where the stratosphere is in a very predictable state, and these get called windows of opportunity because they're a case where you might have even greater predictability coming from the stratosphere. And then an example of that is after a major SSW. You remember that long persistence time? Well, after a major SSW, you can't have another major SSW until you've re-established the vortex and gone through all kinds of precursors. And so you know you're not going to have another major SSW. You know you're stuck in that negative stratospheric NAM state, that weak vortex state, for 1 month, maybe 2 months. And so you know that that's going to bias the tropospheric NAM and the tropospheric pattern toward this particular state in the weeks that follow. And that's an example of a window of opportunity coming from the stratosphere. And sometimes you get similar effects with a strong vortex. So I've spoken a lot about the NAM, but the NAM is just one part of the flow. It only explains somewhere between 20 and 30% of the hemispheric variability in whatever field you're looking at. And so one of the ways in which we can understand a little bit more is to look at regimes. Now, on a simple level, regimes are just recurrent patterns in your anomaly field. And typically they're defined in terms of the 500 hectopascal geopotential height anomalies over some sort of reduced domain of interest. And so they're things that you expect to see recur when you look at these anomaly maps. And so what's shown here, the figure on the left, is the North Atlantic regimes, of which there are 4 during winter. NAO minus, NAO plus, Atlantic Ridge, and Scandinavian blocking. And I think they've become quite famous over the last decade. Less famous, but hopefully as a result of some of the work I've been doing, more famous than they once were, are regimes over North America. And those are also shown here. Arctic High, which is essentially the same as the NAO minus in the left-hand panel, Arctic Low, Alaskan Ridge, and Pacific Trough. And so we can, the next question is then, how are these influenced by the stratosphere? So, well, what we can do is compute the probability of these different regimes during different stratospheric vortex states, when it's weak and when it's strong. And this slide always makes me think of the French flag because of the colors. Anyway, but what that enables you to see is how the probability of these individual regimes changes depending on the vortex. And so looking at this left-hand panel, which is from a paper led by Andrew Charlton-Perez in 2018, you can see that, for example, the NAO minus is about 7 times more likely when the vortex is weak versus strong. You have NAO plus and Atlantic ridging in the next 2 sets of bars are more likely when the vortex is strong. And then Scandinavian blocking actually about equally probable regardless of the strength of the vortex. And then in an equal measure for the North American regimes, Arctic high, much more likely, about 7 times more likely when the vortex is weak versus when it's strong. Arctic low and Pacific trough, more likely when the vortex is strong than when it's weak. And Alaskan ridging, about invariant. So there's a few things which are interesting there, but the one thing that I really want to bring out, really you can get by looking at the left-hand panel and looking at the red bars. So these are the probability of the 4 different regimes when the vortex is weak. What you'll notice is that they're not that dissimilar from each other. Yes, they vary, but you've got things like NAO plus being about the probability about 0.2, NAO minus 0.32, Scandinavian blocking almost the same probability as NAO minus. So the difference in the probability of different regimes in the same vortex state is less than the difference in the probability of a single regime in different vortex states. I'm aware that that was a lot of words. But what that means is that when you have a specific vortex state, it doesn't exactly tell you a specific outcome. You can have this spectrum of tropospheric responses. And so that's still useful information that we're getting from the stratosphere. We know that when the vortex is strong, that we're much less likely to have NAO minus. But it doesn't exactly tell you the specific regime. And that's where other processes in the troposphere are important for driving the formation of these different regimes. You can just think of the stratosphere as providing a nudge towards 1 or 2 specific regimes. Or in the case of the Scandinavian blocking and Alaskan ridging, which are also shown here, they're equally likely. So actually the state of the stratosphere doesn't seem to tell you anything as to whether this is more or less likely than not to occur. And so that's giving us a more complete picture. That's helping us understand that when the vortex is strong, we know that, for example, there are these specific regimes, these specific flow patterns, which are more likely to occur. It still doesn't give us the full answer, and perhaps that's what we're going for. But this is part of the reason why, for example, there was a major sudden warming last winter, and the UK didn't see a cold wave nearly on the same magnitude as what happened in March 2018 following the SSW in February 2018, because we have this spectrum of tropospheric responses. So quick recap before I get into the last sort of section. The polar vortex varies in strength largely due to the breaking of upward propagating Rossby waves into the stratosphere. Sudden warmings are an example of an extremely weak warm vortex, or the complete dissipation of the vortex during winter, with effects that typically last for months. The anomalies in the polar vortex strength are persistent. They're much longer lasting than day-to-day weather, and that's useful. We can use that. The strength of the vortex is one factor, just one, which modulates the northern annular mode and the probability of different weather regimes. And as I said a few years ago now in the talk, I said the strength of the winds 30 kilometers above your head can determine whether you wear a hat and a scarf today. Perhaps it's not so simple, but it is one thing that can ultimately alter the weather you experience and whether or not you wear a hat and scarf. And so the combination of this slowly varying stratospheric state and the knowledge of the impacts on weather regimes and on everything that goes with that, on wind generation, on solar, on mortality. Recent study that I was a part of, we showed that actually there's a significant increase in mortality associated with the occurrence of sudden warmings in the UK. This can yield useful longer-term forecast skill that we can use to plan ahead beyond typical weather forecasts. So the next question: how well can we predict the stratospheric state ahead of time? It's all well and good knowing that once you're in a sudden warming that one's not going to happen, but how well can you predict that one's going to happen in the first place? So what I'm showing here is a figure from Daniela de Meyson's 2020 paper, which shows a set of different forecast models, forecast prediction systems, and the percent of forecast ensemble members accurately predicting strong vortex events or SSW events at various different lead times. And what you can see, the black line being the multi-model mean, that what you can see is that generally this is limited to about 2 weeks. And part of the reason for that is that this is limited somewhat by the predictability of the troposphere. We have this issue whereby sometimes synoptic scale variability, of which we're kind of limited to about 2 weeks, is important for the vortex variability. And so we're a bit limited with how well we can predict that beyond the medium range, and therefore its effects on the stratosphere accurately. And another component is actually the effect of model biases. These models aren't perfect. They have issues. They have issues with biases in the mean state where they don't quite represent processes correctly, and also issues with resolution, which is getting better now that we have more computer processing power. So overall, we're looking at around 2 weeks to accurately predict specific events. There is sometimes skill a bit longer than that. Then sometimes there is skill much less. So I wrote a paper on the 2018 warming and how this was very poorly predicted ahead of time because of some synoptic scale variability, which was very difficult to predict ahead of time. What this means, though, is that if you can predict something like this 2 weeks ahead of time, then with the impacts 2-3 weeks beyond that, you still have this longer term predictability. So it's not a complete write-off, but it would be beneficial, and there is certainly a lot of work going into trying to extend this skill horizon. So this is the last couple of slides, where I'll just look at the winter of 2021-22. So this winter we've had a La Nina and something called an easterly quasi-biennial oscillation. Now the QBO is a band of winds in the equatorial stratosphere that alternates every couple of years or so between westerly and easterly phases. And when the QBO is easterly, what that means is that waves propagating up into the stratosphere, one of the ways in which it can influence the weather anyway, is that waves propagating up into the stratosphere are focused more towards the stratospheric polar vortex, where it can disrupt the vortex more. And so if you've got a more disrupted vortex, then you are more likely to have a negative annular mode, negative northern annular mode in certain weather regimes, and you might have cold weather in the UK, for example. And so the figure on the right is from Amy Butler in NOAA in Colorado, and the x-axis is the Nino index, so negative values are La Nina, and the y-axis is the QBO. And 2022, we're somewhere in this bottom left-hand quadrant, which is rare, but it actually has the highest risk, statistical risk of an SSW. So before this winter happened, looking at this statistically, everyone thought maybe this is a winter where actually we will have a weak vortex and a major warming. But that's not happened, and it doesn't look like it's going to happen. The vortex has remained very strong. That's the magenta line in the left figure, and the right figure showing the forecast from ECMWF, the thick red line on the right-hand figure being the average, so we're way above average. The vortex has just been strong, and so we've had mostly positive annular mode conditions. We're expected to have positive annular mode conditions. Places like the UK have not seen snowmageddon, and parts of the US as well have also seen very, very warm conditions. Why? Very briefly, the amount of wave activity being generated by the troposphere has been unusually low. And so that's shown in the figure on the right, which is the 45-day running mean long wave heat flux at 300 hectopascals, so at the top of the troposphere. And the average, the historical average, is the black line, and then 2021 into 22 is the blue line. And you can see in November and December in particular, it was way down compared with average. What you can also see is recent years where we've had a major warming, as identified by the red arrows, and just how much more elevated that wave activity was. And so even if you've got everything else right, even if you've got an easterly QBO, even if you've got other factors that are suggesting you're going to weaken the vortex, there's just not been many waves going out of the troposphere. And that's largely because we've had a tropospheric pattern that has destructively interfered with the stationary waves and suppressed the wave activity. We've had troughs where we should have had ridges, and that's, as far as I can tell, the important reason for why we've had a strong vortex this winter. And so to wrap up, the polar vortex is a normal feature of the wintertime stratosphere. It's not something new. It's not something that the media should have really got all hyped up about. The Arctic vortex varies on timescales of weeks to months, which makes it useful for sub-seasonal prediction. Now, subseasonal prediction is where the lowest skill currently exists, and there's a lot of work going on to try and understand how we can use the stratosphere to increase that. The probability of different tropospheric weather regimes is significantly altered depending on the vortex state, and that gives us a greater understanding of the weather in a region than just considering this variability of the annular mode. The state of the troposphere, by its modulation of the stationary waves, can influence the strength of the vortex. We've seen that this winter. Weather forecast prediction systems can capture these dynamics, but not to their full extent, in part due to the effect of some biases in the model. There's a paper which Zach Lawrence has been leading that should be going on discussion for weather and climate dynamics soon, which quantifies some of those biases. So watch out for that. And the polar vortex essentially is just one driver, one modulating factor of winter weather and climate variability. It's not always the most important. And sometimes, maybe it doesn't even matter at all. And a good example, just to end on, is December 2010, the coldest December on record for the United Kingdom. Historic event. The vortex was normal strength. So it's not always the be all and end all. I'd like to say that the easiest way to learn more is just to look at the forecast. I think looking at the forecast is useful as an amateur, as a scientist as well. I think that's really how we learn about how these things are evolving. I did write an insights piece for weather, which I wrote before I became editor, which you can check out as well, which is online. And with that, thank you very much for listening, and I'd be more than happy to have some questions.
Thank you, Simon. You just have to imagine the rapturous applause from our audience. So I've got a couple of questions, but it'd be more fun to hear from our audience of 75 people. So if you do have any questions, I realize there's a lot of applause coming through the chat now. But if you do have more questions, then put them in the chat there. We can crack on. An easy one to start with. Earlier on, you showed that picture at the beginning of the tornado.
Yes.
He was asking, what is the book called? I think they're interested in reading it.
I believe it's an introduction to meteorology. It's the second edition. I think
that's by John Shonk, right?
Yeah, John Shonk.
Yeah.
John Shonk.
Cool. Hopefully you'll be able to find that, Dee. I'm going to move over to one of my questions now, because I'm quite interested in this. So you talked about the fact that the SSWs are quite poorly forecast. I wonder whether, is there a significant lack of observations such that if you improve the stratospheric observations, that would be the best way to improve the forecast rather than improving the modeling? Or if the triggering for these is upward propagating Rossby waves, would you expect if there were more vertical profile observations, for example, in the troposphere with radiosondes, would that have the biggest impact on forecast skill, do you think?
I think that's a very good question. I think my general response is that I think this is more an issue of the ability to represent that in a model than the ability to have the data. As things have got better and models have been able to have more vertical levels and a greater vertical resolution, so the ability to actually represent that sort of high frequency profile, then the predictability is increased. But I don't necessarily think that having a better observation would have a huge impact. What it might do actually is have a more kind of secondary effect in that if we could get a better understanding of the vertical profile, represent that, say, in a reanalysis and go higher up beyond the stratopores into the lower mesosphere, then through historical analyses, we could understand better these events. But I think from a real-time operational predictability perspective, I might not be right, but I don't think that's where the issue lies.
Interesting. Thank you. Okay, next up, Jim has asked your figure, which I believe this was asked around slide 13. So I think it was that slide. Your figure that shows time against the temperature anomaly suggests that warming may be a common result even to 1,000 hectopascals. So it's not closely related to cold, I assume.
So if I'm getting this right, and this is where the challenge that comes across is, and believe me, it's even harder sometimes when you're talking to journalists. The warming is contained to the within the polar vortex and to within the polar cap. So when we have our cold air outbreaks that follow major SSWs, that's sort of around the mid latitudes, but the Arctic is warmer in those scenarios. And actually, when the vortex is strong and cold, that's when the Arctic tends to be colder, and we have the milder air. So that warming is essentially, you can almost think of it as like an adiabatic plunger going down through the polar vortex all the way to the Arctic troposphere and warming that column. But it's the disruption and the equatorward sinking of those jet streams that leads the mid-latitudes open to cold. So actually, it's this kind of very challenging communication standpoint, which evidently I didn't quite get to, which was that a warming for us in the mid-latitudes tend to lead to a cooling. A warming in the stratosphere, a warming of the vortex leads to more cold. Which, yes, is a difficult thing to get across. Hopefully that was the question.
I think so. If not, Jim, you can always come back in the chat. Okay, next up, Natalie is asking, by itself, can the stratosphere be useful for subseasonal prediction in the troposphere, or is it just completely dampened by the inherent tropospheric chaos? This is a very good question.
It is a very good question. I believe it's actually just inspired by the last sentence in my thesis, which is kind of how I concluded it. It's the idea that I kind of came to a conclusion from my PhD that just knowing the stratosphere alone isn't enough for accurate, meaningful subseasonal prediction. And so we see that with those regimes, and what I tried to explain with the regime framework, which was that you probably need something else, because just knowing the stratosphere, just knowing it's weak, doesn't give you the answer of which regime you'll be in. It just shifts those probabilities. So I think that by itself, no. And I think we're pushing more in the community toward thinking of the way in which the troposphere is important for the impact of the stratosphere on the troposphere, and starting to maybe think more of the atmosphere as like a 3D, 4D continuum, which is important.
Yeah, definitely the interactions between layers. Great. Next up, Luis says, how global warming could affect southern stratospheric warming episodes?
It's another great question. So part of the difficulty with this, at least at first, was always that running climate models with the resolution to fully represent the stratosphere and to get these warmings accurately represented was always computationally very expensive, very difficult to do. But we're now at a stage where we can do that. We're much better at it, and it's still somewhat unclear. So the stratosphere is radiatively cooling under global warming because of the effect of increased greenhouse gas emissions, increased greenhouse gas concentrations. If you increase carbon dioxide, it warms the troposphere, but it cools the stratosphere. Now, that's just a radiative mean state change. That doesn't mean that the polar vortex itself gets colder. What it could do is extend the season over which you have a vortex. If that gets longer, then you might be able to fit more warmings into a winter. You might have more occasions where you have 2 SSWs per winter because you have a longer season over which to do it. That's one possible aspect. It's also possible that if you change the jet stream in the troposphere, say as a result of Arctic amplification of global warming, that you change the amount of waves and the characteristics of those waves that can propagate up into the stratosphere, and that could affect it too. But I think, at least my understanding is that it's currently not entirely clear, and it is a bit more one of those more uncertain effects.
Definitely, yeah. More research needed, as always. Just to acknowledge that Sarah also asked that same question as well. So, okay, next up, William is asking, I thought that the sequence of very deep low pressures in the northeast Atlantic could trigger a sudden stratospheric warming So hence a reversal of the westerly flow at 10 hectopascal and the threat of a beast from the east. Is this too simple, or is it even incorrect?
It's somewhere between, it's probably somewhere between the two. I think that you often need, in often cases there have been times where you have a synoptically active pattern in the North Atlantic to generate waves and wave breaking in the troposphere that can propagate vertically, and also this idea that if a sequence of low pressures in the North Atlantic, that's a positive North Atlantic oscillation, and that tends to be associated with having a stronger vortex. And actually, I'm on the right slide here because you can actually see that before this weak vortex event, at least in this composite, maybe there is a suggestion of a strong vortex preceding that, these blues at a lag of about -40 days. There are some, not every sudden warming, but in some cases, sudden warmings are preceded by a stronger vortex and a positive NAO. The 2018 SSW, certainly that was the case. So that it's not always the case. So maybe it is too simple, but I don't think it's incorrect. I think that can happen. But I think the thing that you should look out for is things like Scandinavian blocking. That's a really common precursor of major warmings.
Excellent. I think that might be a case of following Simon on Twitter to get more commentary on that topic.
Yes, yeah, please follow me on Twitter if you're interested more.
Yeah, I'm not sure if you want to go back to your final slide to show off your socials.
I think it was my titles. It was the title slide that had this actually. But yes,
I'm going to sneak in one of my own questions here. This is quite a random fire question, but have you come across or like explored polar vortexes on other planets?
I haven't, but people have, and people do, and they have all kinds of strange shapes depending on the waves. I think is it right that there's a hexagonal vortex on Saturn?
Yeah, on Saturn. Yeah, that's the one I was thinking of. Yeah, I wasn't sure if you knew anything about the dynamics and how it compared.
Planetary atmospheres. No, I don't. But I now work with people who do, so maybe I'll pick some of that up.
Excellent. That's another follow on Twitter then. Okay. Matt also asked about how sudden stratospheric warmings will change under climate. So I think our last question is from John, who asks, is there any correlation between polar sea ice extent and stratospheric behavior in either direction?
There is. So that's another one of the ways in which climate change could lead to changes in sudden warming behavior. There is evidence to suggest that perhaps one of the most well-defined phenomena is that it's particularly reduction in Barents-Kara sea ice leads to an amplification of ridging in that area, and then that has an effect on the wave structure and weakens the vortex. It's always been somewhat contentious, but I think there is evidence to suggest that it has at least some effect. It's just whether or not that signal is kind of loud enough to really be noticeable above the noise of everything else that's going on in the stratosphere troposphere system. But if you follow people like Judah Cohen, he had a paper recently out in Science that was relating this to changes in the strength and structure of the vortex and trying to relate that to cold air outbreaks over North America. So yes, there is, and sea ice loss is one key way.
Excellent. Right, we have one more question that came in last minute there. Isabella is asking, the polar vortex can be split or displaced. What causes one or the other? Does this have an impact on the troposphere?
Great question. So the first answer to the first part of the question is generally it depends on how the wave structure is amplified. So using this figure as an example, if you look at around 100 hectopascals, you'll see that there's two ridges and two troughs. And this was actually a development of a wave number 2 disturbance. And two ridges, two troughs translates quite naturally to a splitting, because that's the split is two troughs, and then you have two ridges kind of pincing it in. And indeed, that's what happened about 6 days after this figure. There was a wave number 2 event that split the polar vortex. And a wave number 1 it tends to lead to that displacement. So it often depends on how the waves have been amplified, and some of that comes from how the troposphere forces these waves. Some of it comes from how the stratosphere receives the waves. That was the bit I didn't quite get into, which is that the stratosphere itself can control the behavior of these waves. Yes, sometimes that can have an impact on the troposphere. In general, it's often been said that splits have a larger impact on the troposphere, but it's not necessarily clear that that's just because they split, and perhaps is because they're actually just slightly more extreme. They tend to be associated with stronger easterlies, with a much larger, deeper warming of the stratosphere. So I think that's the case. Yeah.
Great, very comprehensive answer. That then wraps us up. That's all the questions we have. If you do have any more questions, please feel free to contact us via the methods on screen in a few seconds. Thank you again, Simon, for presenting this evening. A very informative talk. Yes, these are our socials, which you can contact us on. So if you do have any more questions, contact us through there. I'll leave this up at the end as well if you need to write them down. You will be able to rewatch this talk on the YouTube channel, the RMetS YouTube channel, where it will be uploaded hopefully in the next few days. Our next talk will be in February. This is our annual PhD showcase, where we have 3 PhD students from Leeds come and talk about their work in shorter talks. That is in progress. We've selected our students, and the details for that will be coming out on the website and in the emails that we send out in the next few weeks. So yeah, look out for that one. So finally, just thank you again to Simon, Dr. Simon Lee, for giving us this wonderfully informative talk. And thank you for the RMetS organisers behind the scenes, especially to Kelly. And finally, a big thank you to all of you for attending this talk tonight. Thank you and good night.